That's gone 1 o'clock, I might as well get going. For those of you who don't know me, I'm Alisdair Meredith. I work at Bloomberg in New York on our implementation of some of the low-level standard libraries. And for my sins, I'm a former chair of the library working group for the ISO Standard Committee, so I've got a bit of an idea of some of the things we're talking about today. This talk is essentially on implementing tuple in C++20, and this is not so much how your standard library vendor is likely to implement tuple, but this is if I'm implementing tuple afresh, brand new today, with all the features of C++20, how I might choose to implement it, which is coincidentally something I happen to do as a personal exercise every time a new version of the standard comes out. So this talk can be seen as two ways. It's a tuple talk using C++20 language features, or is it a talk about tuple, C++20 using tuple as an example? So just a quick check for me for hands, who thinks they're here to a talk that's mostly about tuple with some C++20 in it? And who's here for a talk about C++20 with a bit of tuple in it? The majority, are luckily in the direction I'd planned the talk. So if this is not what you intended, this is your quick chance to run for another room. We will talk a bit about tuple. It's the whole focus of the examples. But the essence of the talk is to illustrate a lot of the new features coming out of C++20. Now, specifically in the past, has anyone seen talks I've given in the past on tuple? Okay, so I might need to talk a little bit more about some of the things I was going to take for granted. So C++20 in general, we've got a bunch of big ticket items coming through that are hopefully going to excite a lot of people. I think C++20 is going to be at least as disruptive as C++11 was. It's a huge change coming down the line at us. And just for convenience, it seems that C and 0 are a big deal about this language. So big things coming down. We've got concepts. I'll go through here. We've got concepts we're going to hear about in this talk. We've got contracts, which are kind of the runtime analog to compile time concepts, which don't feature so much in this talk. An awful lot of enhancements came through for const expr. So const expr is a C++11 feature that came with quite a few restrictions. And almost all of those restrictions are gone by the time we get to C++20. Not quite all of them, but it's almost the full runtime language is available now. Coroutines are another big deal that don't have a whole lot to do with tuple, so we'll not be talking about them. We've got this funky comparison operator, and I couldn't get a C0 into modules. I'm trying. Codules doesn't work. Components feels like it's cheating, but yes. And there's a bunch of other things that aren't so much on the big headline, big ticket items that people look for when they see C++20. But a bunch of other little changes, incremental changes that have a big impact on how I might implement and deploy tuple. So I have a quick mention of modules. Modules don't have a direct bearing on tuple, but they do have a bearing on how I might write libraries in the future. They have been distinctly, we got user feedback from Twitter and various other surveys that people are saying, modules is what they want. We want to move into a better world than hash include, token pasting millions of lines of source into every translation unit. So it's essentially a better way now we're able to build and access libraries without relying on the preprocessor to get access to the interface. It may still require full access to the original source in order to build the module interface. In the same way that you had to distribute header files, you're likely going to have to still distribute source files for the compiler to build the module and then use its cached implementation of what it did with that module. So it's not a binary module distribution format that we're looking at, just to set expectations. But the real benefit we get with implementing standard libraries today now is that we'll be isolated a lot from user injecting of macros. So here's the basic outline of how I might write a module. First of all, I have the module keyword. Then we get this thing called the preamble between this is a module translation unit, and here I'm going to actually say I'm exporting a module called tuple. In between here, in the preamble, I can declare my dependencies. And I can either import a module the same way as I would with regular code going forward, or I can hash include, same as I would before. But the hash include is subject to some new rules. In particular, if I hash include, it's treated like an import, so that macros defined here do not leak into subsequent includes or imports, just within the preamble. And that change means that I now do not need to worry about users colliding their macros with identifiers in my code. So for free, I now get macro isolation and have much less need to use funky obfuscated names throughout all my examples. So I just now get to write all my clean examples and pretend that, yes, this is actually how you would write a standard library now. It's not true because they have all these backward legacy support to go still. But in a pure module world of the future, we can be a lot freer about actually writing clean, maintainable, readable code. So that's about as much as I'm going to say about modules. After there's my calling out where the preamble is. So going back to the topic of the talk, what is a tuple? Basic idea is a heterogeneous container of exactly n elements, and the elements are accessed by index, get n, and we support the comparison operators if all our elements support the comparison operators. And the mental model is as if I were to write a struct with n data members, and then there's some compile time reflection I can use to query and find out what they are. So basically, we're a data type emulating an aggregate struct with all of those data members, included or indexed by types in C++14. Only better because we're providing comparison operators and a few other features on top. So if we think about this in terms of code, our example is going to be struct data. When I'm trying to use data and I know what it does, I really like to have ID, name, and value. I'm not going to do better than actually having a struct with named fields. This is how I want to use the thing. But if we change our naming, we emphasize structure over content. So my fields are just v0, v1, v2, the first, second, and third field, and I access them now, int, string, double, whatever, is v0, v1, v2, with the same initialization here. So if we switch that now to being a tuple, it's the same idea. I'm just using get 0, 1, 2. I no longer know the names of these fields, but we're indexing and accessing through structural notion of what the data is rather than content of the fields. If this structural notion is useful to you, that's where tuples are great. And in particular, because this is all now just by index, which is easily meta-programmable, tuples are very good for glue in generative frameworks where you're trying to generate code to pass on to the next thing down the line. In C++14, this reminder allows us now to index by type as well as by positional index. If I had tuple with 2 strings in it, does everyone know what would happen when I tried to get the string out here? Okay, very simple. It's an error. It's an ambiguity because it doesn't know which string I mean. So we don't kill the whole feature, but we say if the type is ambiguous, so I don't know which index you get, you're going to have to tell me the index yourself. So, first question, why is get not a member function? Why is it a free function? So does anyone have any hint on here? Take a quick show of hands. Anyone understand why way back in the day we decided to make get a free function? It's embarrassing. The syntax for the member get would be awkward if I was in generic code. So if I've just got a tuple and I know what the values are, that's great. If I'm a template and I'm passed an arbitrary tuple, we have to use this funky .template syntax. So the compiler knows that's not a less than operator when it sees get, when everything is still type dependent. So that was fairly horrible. But it got worse. In C++03, if you used the .template but you weren't in generic code, that would still be an error because you could use .template only when it was required and had to think like a compiler. And tuple was designed for standard library TR1, which was designed against C++03. So for this reason, we said get is going to be a free function And that was that. So that's our embarrassing history about get. And the nice thing is, in C++20, without the .template, this will start to just work now. Because we might relax the rules in C++11, we relaxed the rules that said you can use .template and type name only when they're required. The compiler will now ignore redundant versions of those. You've now gone the other way and said, you know, an awful lot of compilers are now giving this error message that says, you needed to put .template there. I know what you meant, now go and do it. And this kind of gets annoying to say, well, if the compiler knows what I mean, why can't it just do it for me? So we finally relaxed the rules that require type name and .template everywhere in independent context. Not 100% of the places, sometimes the disambiguation is still necessary, but in this case, when it sees t.get less than, first of all it says, can I resolve this as an operator less than lookup? It says, oh, no I can't. Maybe you meant a template, I'll try again. And then it tries and finds, oh look, there is the right answer. So obviously that's what you intended. So we finally get to relax some of these awkward rules about where you have to use funky syntax in C++ templates to make them that bit more approachable. So moving on, what actually do we have within standard tuple? Mostly we have a bunch of constructors, destructor, assignment operators, and a swap member function. It's a data type that holds data. There's not a lot else to it. Everything else is out here as free functions. We have, since C++17, deduction guides. That's where comparison operators go. Even the access of the get function is a free function. And then assorted utilities such as tupleCat and make things to combine and construct tuples for you. As far as this talk goes, we're going to talk about the white stuff. Allocator-aware constructors just get messy, so I punted those out the talk. Not a whole lot to say about defaulting the destructor. The deduction guides were added in C++17, and nothing has really changed there. If you don't know what they are, come and talk to me after the talk. And likewise, the assorted utilities were applications of tuple address wasn't going that. We've got 90 minutes, I can't cover everything. And a quick recap of where tuple went in C++17, because I'm not assuming everyone is currently up to date. First of all, we have const expert all the things as a general notion of adding const expert to as many places in the library as were reasonable. So large parts of the tuple API that weren't const expert in C++14 became const expert in C++17. You'll see this much more widely through the C++20 library, especially, as I say, we've relaxed an awful lot of the things you couldn't do in const expert, such as changing the active member of a union, or doing a dynamic cast on a polymorphic type, or calling a virtual function. These things are all allowed now. You're even allowed to put try and catch in a const expert function, just don't actually throw an exception in the const expert evaluations. Conditionally explicit, we'll talk more about later, is the idea that we've got all these constructors. That, as we said, there's currently 18 constructors. Oh, it looks like 18. We have this conditionally explicit notion that says most of those constructors come paired up. One version is explicit and one version is not. And then we use some wonderful SFINAE magic to say, if when I called that constructor, I would be calling an explicit constructor of one of my members, then that constructor should be declared explicit. Otherwise, that constructor is not declared explicit. So we have both, and arranged with clever SFINAE tricks that only one of them will ever be selected. That was fun. And in general, we put stronger, everyone knows what SFINAE is as a constraint to say, if this constructor or method would not instantiate correctly, then make it drop out of overload resolution and not exist at all. Previously, you could indicate errors however you like, including, I'll let you call it, I'll let you instantiate it, and then you'll get the error to say, no, this thing wasn't copyable. Now, if I've not got So C++17, if my members aren't copyable, then I don't have a copy constructor, and so forth. And finally, we had this wonderful CTAD thing, class template argument deduction, which is what we talked about the previous slide with the 5 deduction guides. This just says I can initialize a tuple from a bunch of data members, and it says, you know, I can deduce from those arguments you gave me to the constructor what the template parameters are of the tuple itself. So I can now just use tuple without any angle brackets, and from the construction, it will deduce exactly what kind of tuple I wanted. That's all C++17. And there are a bunch of C++17 language features that helped in implementing and doing various things with tuple, or especially some of these come more to the fore in C++20. Fold expressions was a big one, which I'm about to talk about. Sorry. If const expr is a neater way to, when you're implementing a const expr function, to say, if I can do it const expr, use this, otherwise, I can go, if based on some trait, I can say, I've got some property, I can do one branch, otherwise do the other branch, rather than having to dispatch out into multiple overloads. They rewrote the rules on inheriting constructors, which solved a lot of corner cases that now make them more usable in some contexts that happen to be useful for us. We guaranteed copy elision, which wasn't a big deal for tuple in C++17, but might help in some of my design. And we added in C++14 this index sequence library. We're going to come back to that a little bit more as well. But first of all, I'm going to talk a little bit about fold expressions. This is a C++17 revision, but it's something that I stumbled into enough errors with that I thought it was worth just calling out as a public service. Fold expressions come from functional programming languages, and they allow us to fold a pack expansion where the pack expansion is a lot of commas. With a fold expression, we can now combine different operators in that position. And this is the grammar, color-coded, just because I like color-coding things. So we've got 3 possible ways of writing them up here. Here's a set of operators that we can use in a fold expression, which is essentially any operator other than new, delete, type ID, size of, align of, and the ternary operator. We can't do a fold over ternary operators yet. Dot. Dot? Is dot an operator? You
can't use it in a fold expression, it just wasn't in your list.
You're correct. I didn't think it was, I was thinking it was part of the grammar rather than an operator. So I stand corrected by our current esteemed library working group chair. Thank you. And then we have these unary expressions drop in, or cast expressions drop in here, and these are these things. But the main reason I'm pointing out this slide is this thing up here. This is where I always make my incredibly common error with fold expressions, which is those brackets are not redundant. They are a part of the grammar. And I will always write my fold expression and then get some really strange, incomprehensible errors coming out of the compiler. You know, I've just had to learn till it becomes instinct. Did I miss a redundant pair of parentheses to say the thing in there is a fold expression? So that's my public service announcement. This is the error that you will keep making, and you will not grok from the error messages the first dozen or 2 dozen times you do this. So moving on to some of the C++20 features that are going to impact my idea of how implementing tuple gets a bit simpler. Here's the big grab bag list. I'll not walk through it now. We're going to walk through them more in turn. The last one at the end is a library function, make object using allocator. I'm not going to talk about that because I ran out of time on my slides to actually get into the allocator-aware constructors, but we have some additional library support that will help even that part of the design. And I'm going to start with, it says generic implementation here. I'm looking specifically at the comparison operators and swap. And this part is going to be a complete non-standard extension just because I like to write things as simple as I can. And I don't want to write these things multiple times for tuple, pair, and array when the tuple interface seems to provide sufficient genericity but I can provide a single implementation of these, and it should just work. So that's where I'm going to start. We're actually not going to implement tuple yet. We're going to implement the comparison operators and swap for anything that supports the tuple-like interface, and then for free, I've got that for tuple when I want it. So implementing comparison in C++ 17. If you look at how tuple is defined, then pair and array for their overloads, we've got 6 comparison operators, which are just, the standard equals, not equals, less than or equal to. They're all defined only in terms of operator less than and operator equals. And the other 4 are then synthesized from those 2, which has a bearing if you've got, say, a tuple of float. Operator equals when or operator doesn't equal when my float contains a nan will give me a different answer than comparing not equals on the float itself. So it's subtle, but sometimes these differences will show up. So, what's my basic implementation? Hopefully this code is still readable on the screen. From where I'm looking here with the bright lights, some of that's looking a bit faded. Is that code readable? Because if it's not, we're going to have a really rough rest of the talk. So, I've got comparing 2 tuples. We've got a parameter pack T and a parameter pack U because it's a heterogeneous comparison to different tuples as long as their elements are comparable, can be compared. And because I want to do something per element, I'm going to use this index sequence 4 standard library function or type that comes out of C++ 14. It's actually a type, so I'm going to make one by value just in place and avoid vote selecting path and everything. I just prefer to use brace initialization. It simplifies the set of things I have to worry about. And I'm going to call some implementation function called requal. And that will then walk over both of these tuples in parallel and give me my answer. And I showed how to do this in previous talks, so I'm going to move on to the general interface before we actually go and implement the impl function. But given I want to be generic here, where this could be walking over an array, standard array or a standard pair, and this is very conceptual just as I go along, we're now going to have T and U. So it could be anything that just happens to support the operations I need. And again, now I no longer have parameter packs because T and U they're just regular types. They don't have parameter packs built in there. I make a different alias here. I call make index sequence on tuple size of T. And tuple size will say, well, I'm somehow going to have to constrain these both to be the same size. So here's how I simply constrain both to be the same size in C++ 17. Isn't that delightfully simple? Okay. Why am I doing this crazy complicated thing? Well, first of all, I really want to constrain this to, I'm providing a generic operator equal that compares anything. I really don't want to be grabbing comparing ints and things. Now, this just should be working with tuple-like things. It should be working with tuples that have the same arity. I tried my usual tricks with enable if T on the result type. That's where I would normally put a constraint. And for whatever reason at the time I was doing this, Clang was giving me errors. I couldn't quite convince myself it was a bug in Clang or could convince myself it was a bug in my code. Sometimes when you go down these SFINAE dark corners, you end up in dark corners with the standard. Sometimes it's easier just to provide a different solution than try to figure out who was right and wrong. So I didn't follow the bug report, I just moved on in this case. So, we're back to this thing where you've got a pointer to a chart array which has size either 0 or 1 because tuple size equals tuple size is a bool. And if they're equal, I get the bool value 1, and that's a valid array expression. And if they're 0, I'm trying to create arrays of size 0. That's not allowed, and it's a SFINAE constraint. So then the thing just drops out. And I use default argument equals null putter. Everything's good. This does what I need it to do in C++ 17. I did try using the _v variable templates that we had in C++ 17. And that turns out to give me a hard non-SFINAE-able error. When I do something like this, tuple int true is equal to 1, well, 1 doesn't have tuple size defined. And tuple size underscore v is defined as being the value found within the tuple size template. And that's a second recursive instantiation lookup. And in order to have some limits to the complexity of arbitrary compile time lookup on these things, the rule is, if a SFINAE constraint fails at the first deduction, it's a SFINAE constraint. If it's got to do subsequent instantiations, it's a hard error. So I can't actually use the underscore v form to simplify this just a little bit. So I end up having to go back to that original formulation actually. The original formulation actually, sorry, I'm having trouble with my new teeth. Sorry about that. My original formulation here with the funky array pointer, and that just works. But it's ugly, and that's C++ 17. Oh, the other one I'm doing here is what looks like a function call. I'm actually calling the default constructor, because not using curly braces just because I like this thing to look like a function, even though in practice I'm making context per integral constant objects and then comparing their values. So that's another hidden detail that makes it look nice and it all just works. Relatively nice. So now I've got this funky syntax. I can implement the R equal function. And here we have the whole reason I'm doing the delegation is I want to be able to do get of index. But for that, I need a parameter pack of indices that's the same length as all the types in order to match the index to the type. I can't extract that information here, so I have to go through the level of indirection. I can deduce the indices from this make index sequence call. And that now means I have a corresponding number of indices to be able to call get on each of these elements in turn. I can now use my fold expression, C++ 17 to the rescue here. And remember to put my redundant parentheses in here. This is where I hit those errors far too frequently. And that just works. That's C++ 17 doing this. So let's see if we can clean it up a little in C++ 20. One of the first things I tried doing was I like using my default function arguments and move things out of the way. And it turns out this doesn't work. Sorry, I'm showing on with a belt-fitted microphone. This one's giving me too much trouble. Does everyone understand, or can anyone see why this intuitive, I want to just deduce my index sequence and not have to specify it every time is not going to work? Because this is a common idiom you use when, for defaulting arguments on template parameters. But the trouble is, this is a runtime argument, not a compile time argument. So I can't do the deduction in this case because at the time I'm doing the deduction, I don't know what the argument is. So this is not a deduction context, so I actually have to continue passing that down here. So this was just a slide highlighting my own foolishness, a common mistake. I keep making this mistake. So if you're ever into this thing and you're thinking, why is a compiler static me trying to do something simple? You cannot deduce from a defaulted runtime argument.
Why would we try to do that in C++ 20 class days?
And that's not specific to C++ 20. It was part of the simplification I was trying to get to. And that's just where it landed on the slide, sorry. I made the same mistake in 17 as well. But we do see my first attempt to go into 20 down here, where we've got these funky things called TupleLike and requires. So I'll jump forward 2 slides, I think, to get back to that. So the idea here is now I'm trying to use C++ 20 concepts to simplify my work. I'm going to define a concept called TupleLike. And it says this type, whatever it is, has an interface a bit like tuple. If it has that interface, it's going to match and this will be a valuable candidate in overload resolution. But if the type T and U that I see here in deduction do not satisfy the tuple-like constraint, then this is just not a viable candidate and keep looking. Now, we also have the requires syntax so that I can use more specific constraints locally. I don't have to put everything up into a concept. And in this case, I just want to require that both tuples, or both T and U, have a tuple size of the same length. And you'll spot I am now using tuple size underscore V. And this will not be the hard error as it was before. Does anyone see why that would be the case? The idea is my tuple-like requirement is going to insist that I have a tuple size V that's valid, or a tuple size that's valid, which satisfies a constraint that would cause tuple size V to fail before. So because I've already satisfied the constraint for tuple-like, I know that tuple size V is actually going to instantiate correctly. So I don't need to do any nice fancy workarounds. I can use the nice simple variable template form here. This is a slide I'm very uncomfortable about because I've not yet had a compiler implementing C++20 concepts to verify that I've got all the syntax correct. In fact, I believe I've definitely got at least one part of this wrong. And I don't know how to fix it. So this is, to an extent, this is a lie. But I would still do something like this. I would just give it a less specific name than tuple-like because it's an implementation sim that will still help me. So first of all, we have something that says tuple size V of T has to exist. And it has to be the same as standard size T. I've run this one past several other concept experts. I'm fairly sure that line at least is correct. And the next one is the one that gives me trouble. I'm trying to say that for every index, tuple element of T with that index and my type T will give me a type name. And it turns out we actually don't know how to say this in practice. I was alluding along the lines of something like this. In practice, we probably can't do something like this. So I might have to give up my concept guaranteeing I can do the tuple element. But that's not the end of the world because I didn't rely on that constraint too much in the examples that follow. It was just something I assumed would be there. And likewise, we then have for calls to get, where I pass an unsigned integer to the index. And again, these standard concepts, standard same, standard unsigned integer, are all defined in the concept header. So this is my notion of a tuple-like type. It's a concept that has a requires. These expressions are all valid. And that's how we would, hopefully there'll be more talks about concepts elsewhere throughout the week, which will go in more detail. But this is the notion of, it's a relatively simple set of constraints, and now we're talking in simple vocabulary rather than crazy SFINAE expressions everywhere else I'm trying to do this. So that has simplified this up a little bit. That's my next slide. So I'm trying to remember my talk through here. I've got 3 or 4 different directions I can go from this point. I'm trying to remember which one's up next. Okay. Another idea we had was simplified concept syntax. The original intent was to have something like this without even the auto keywords. So we would write a function using concepts rather than types, and it's implicitly a function template, where as long as you satisfy the constraints of those concepts, then it's as if you'd written the appropriate template header to do all the same things. Some of us were very uncomfortable that looking at a function declaration, I wouldn't know if I've got, without more detail, whether that identifier is a type name or a concept name, or potentially both, depending upon whatever bringing things into scope. And therefore, I didn't know whether I was looking at a function, which just follows the easy rules of implementing a function, or a function template, which has a few more corner cases all around type dependency and so forth. Or potentially both, depending on how things were called. So the idea is we now have a constraint auto. And it's the same as having a polymorphic lambda, where you use auto just to say, deduce what argument comes here. We can now put a constraint on the auto to say, deduce something that satisfies this concept. So we now have something that is much more pleasing to the eye in theory. We don't have that alarming template head that can scare people. But we've also given up the names of types A and B. So now that I want to say tuple size is these two things have the same size, I've lost the name. So I now have to use decal type to pull out the names to say these things, when I substitute them back into tuple size, produce the same size. Then everything else is the same. It's just a different way of writing the same code in C++20. Now, hidden in all this, I didn't talk about why there's potentially a subtle bug here in C++17. And this would catch me out every time I implement this, because I like to have very strong code hygiene. Nothing that's not absolutely needed gets hash included in my internal definitions. So, when I'm implementing an variable, I do a lookup for get, and I don't find anything, because I've not included the extra header, because this is fully generic code, it's not tuple code. I have no reason to include something that would define get. That might come afterwards, when I'm building my other graph and someone's using tuple. But at the time I define this code within its header, there is no get function to be found. And I would get an error saying the ordinary name lookup has failed to find get. What changes for C++20 is it says, well, I see you're calling get on an index. So that's going to be some kind of dependent lookup. I'm going to potentially find something in phase 2 of template lookup when I do the extra ADL in context. So I'll defer giving you that error. And if ADL in phase 2 then can find that get index, as it's going to be able to do in my full implementation, then I don't need to give you that early hard error. So in the elided code that you don't see at the top, if that didn't include a definition of get, this would have broken in C++17, but it will now work in C++20. And this is a really subtle bug that keeps annoying me every time I implement this. So this, I think, is largely run through as a core defect fix. Doesn't even get a paper resolving it as a feature, but it's one of my biggest welcome features in C++20, because I keep losing it on that one. So again, implementing not equals, very similar to how we implemented equals equals. We just negate calling the same implementation function. Implementing swap in C++20. This might even be a C++17 implementation. Can you see anything 20 specific about this yet? Okay. But it's the same idea. We have swap this time, we just got the same type, because we don't want to swap heterogeneous types, generally not a well-known supported idiom yet. Though some people keep trying to push the idea, it might happen yet. So again, we pass on to our do swap. For swap, we're going to do another fold expression. And because swap is a function that doesn't return anything, there's no easier way to concatenate them, we're going to do a fold over the comma operator. And then we have this extra crazy thing that we're going to cast our swap expression to void. Does anybody understand why I'm doing the cast to void? In case someone overloads a comma. Yeah. Specifically, somebody for their own user-defined type might define swap rather than returning void to return a user-defined type, and then overload the comma operator on that crazy user-defined type, just to screw with library vendors. So we end up having to do this crazy cast to void just to silence people doing crazy things on us. So that's our implementation of swap. But now, is there anything else in C++20 that we might have used on the previous example, could use here, that can help us simplify things even further? It turns out we've made extensions to the lambda syntax. So this lets me do away completely with the implementation detail function. So with my lambda expression, I hate calling lambdas inline because it just becomes a token soup. So I'm going to declare a local variable, auto-impl, that will be of the type of the lambda expression. between the capture list and the arguments, I can now put something that looks like a template head and say, here are some template parameters that help guide can be deduced for what comes next. So this allows me to pass my index sequence as before, introduce a parameter pack. A and B I've captured by reference, so I don't need to pass those in when I invoke the impl function. So I have an error here, in my slide that will now be repeated in all subsequent slides that use the lambda expression. Darn, thought I'd fixed all those. So yes, I would return impl not imp, with just to make index sequence, and then I've got A and B come from the reference capture. So that, compared to that, looks quite nice. It's smaller, it's more compact. I'm not having to leak all these extra implementation detail functions and namespaces. The downside is I can't just delegate the no except. So I'll leave it as an exercise for the reader. It's not too difficult for what goes in there, but I didn't want to spend too much time consuming slide space on that. Always beware when the presenter says exercise for the reader.
Do we have used that for implementing the operator equals?
Sorry?
Do we have used that?
Yes, because you've used this for implementing operator equals equals and the other operators as well. So, as I say, I'm just working my way through a different set of examples and calling out in different places. This one's slightly simpler, as I say, because I can assume that both T's are the same. Next feature, making it even simpler. Expansion statements have not landed in C++ 20 yet, but they have been approved to be passed along and are being reviewed by the core working group. They should land in the Cologne meeting in July, which is the last meeting before we actually send C++ 20 out for ballot. So this is a slight preview, but it is definitely intended to be a C++ 20 feature. And in this case, we're doing away with even the lambda expression and the fold expressions. We're using an expansion statement, which is this new for ... syntax. So the idea here is I'm going to expand out some notion of the contents of the for loop, and that in turn will repeatedly give me effectively a swap get I, swap get, and the idea is it's a range-based for loop syntax we use, and something here has then got to be something that we would iterate over. Now normally this would be something like a parameter pack, such as the index sequence types itself, or something that implements the, I have to move on next slide. Range-based for loop syntax. So you can iterate over only one thing because we can't have two elements coming in parallel from a for loop syntax at the moment, and there's no proposals to extend that here. We can iterate over a parameter pack because the pack expansion, the compiler knows what it's dealing with there, and we can iterate over anything that supports a structured binding. And if we come back to the example I'm using here, index sequence for types, unfortunately, does not satisfy any of those requirements. So I'm now writing a paper for the next meeting to say, if this were to support structured bindings, we could do the last little corner here. Technically, I'm out of time for getting this into C++ 20, so I have no idea how well or badly it will be received. But given that it's interacting with a language feature that's just moving as we're talking, I'm hoping I've got a 20% chance. Marshall will be shouting at me even claiming that. But yeah, the proposal is to extend integer sequence to support structured bindings, which would look like this. Tuple size derives from integer constant of whatever kind of integer sequence you've got and the size of the index. Tuple element is whatever type of the elements are. And then I'm going to cheat for get and just return by value. Because I've got an immutable compile time sequence here. There's nothing else useful I can do. They're all guaranteed to be integral value types, so there's no benefit in trying to return by const reference or anything. So I think a single overload here should work. And my syntax might need a little bit of tweaking, but my idea here is I'm expanding the parameter pack and then just pulling out index I. So that's an initializer with an array something. I might just cast the syntax just so it knows what I'm trying to deduce with the pack expansion. But it's a trivial thing to implement. And then we have the ability, after the standard library, just to index over anything that can be indexed with a numerical index for walking pairs in parallel and so forth. Another example would be implementing operator less than. This is, again, I've got my requires clause in, so this is definitely C++ 20. This makes sense to everyone? I hope not, because it's blatantly buggy. Everyone see the error? The bad news is it will compile. But this is supposed to be a lexicographical comparison. I don't just return and on each element-wise less than. So I've got to do something a little bit more contrived in order to get the original less than to work. Could look something like this. So I can use if const expert to say, if my tuple size is, I've reached the end of the tuple, then everything was equal, and therefore not less than. So return false. Otherwise, return get my current index is less than my current index. If that's true, great. Otherwise, it's not less than. And if it's not less than, it's gone the other way. I can return false. Otherwise, I'm dependent on whatever the result of the next index is. So it's a recursive instantiation. And that will give me the right answer. And I invoke it with is less angle 0 just to kick it off from the first index. So that works. At this point, I presented this as a homework in Bloomberg. They said, I couldn't see a way to implement this using a simple fold expression. Be careful what you ask in front of a room full of smart folks. I was sent the answer, and I was going to print it here, but the even simpler answer is, of course, use an expansion statement. So here we can see a bit more of the benefits of the way expansion statements will work. First of all, if get I of this is less than get I of other, return true. If get I of other is less than get I of this, reverse the order, then we know to return false. Otherwise, we go around and we get the next expansion, and the next expansion, and the next expansion. If we come at the end of the sequence of expansions, well, the answer is false because they're equal or equivalent. So that is, again, expansion statements make implementing these comparison operators, especially in generic code, that much simpler. But that's not the end of the story. We have this funky thing called the Spaceship operator coming into C++ 20. And the idea here is the Spaceship operator is a three-way comparison. It will return if things are equal or equivalent, greater than or less than in one invocation. But you'll notice it's got something funky about the return type. And again, this is something that's moving as we speak, so this hasn't landed in C++ 20 for tuple in the form that you're looking at, but this is expected to be how we implement comparisons in tuple in C++ 20. And it's not 100% backwards compatible, but hopefully only crazy code will notice the difference. Or perverse code where people are getting what they asked for, so they should hopefully be a bit more comfortable if they have to fix things up. One of the changes that's happened, or is happening as we speak, is we still want to provide an operator to equals overload. And the other thing you'll notice is, first of all, we lose all the extra external overloads taking 2 arguments. These things are declared just one way around. Probably doesn't matter so much on tuple, but in general, when you implement these defaulted or these comparison operators now, if lookup fails to find the arguments in one direction, if in a heterogeneous comparison, it will swap the arguments and try again. So you only need to implement these things in one direction, not both, to get symmetric application. So that's kind of nice. The other thing that's happening here that might catch people by surprise is a general trend that's happening in library design now, especially for operators, is these are friend functions that are not members, but they're declared and defined inside the class. And the reason to do this is these functions are not found by ordinary name lookup. So name lookup runs that much faster when you've got, especially generic overloads of common operators. Compile time can get quite large just trying to resolve which equal did you mean. But because they're friend functions, they are found via argument-dependent lookup. So ordinary name lookup is not going to find these things. Argument-dependent lookup is, and that means we should be dealing with smaller sets when we're trying to resolve which of these to refine. And hopefully reduce ambiguities and a few other things, which is where you can get into some of the corner cases where the fact it's found only by argument-dependent lookup and not by regular name lookup and isn't ambiguous. That's some of your corner cases where things will be a little bit different. But certainly as we're applying the new comparison operators, we're retrofitting this style into the standard library. That's not yet happening for things like the streaming operators. So, what does the Spaceship operator return? Well, we're also not, I'm slightly cheating with the equals default here. I'm cheating because these are heterogeneous operations, and I realized after I'd written the slide that the equals default will work only for tuple in these cases. So we still actually have to provide the implementations of these that look a little bit like what we saw before. But we can default for the homogeneous case. Spaceship can return 5 different structs, depending upon how you wish to define comparison for your type. So we've got weakens, and these are effectively ordered as in, this is the least expressive to the most expressive. So weak and strong equality are for things that might support only equality comparison, but not ordering. An example here would be something like standard complex. I can definitely use operator equals equals and operator not equals on a standard complex, but I can't use an operator less than because there's no arbitrary ordering of these elements. And weak and strong is for something like, strong is an integer. Integers, any 2 values compare equal, and you know what you're dealing with. Weak equality would be something like, similar for the partial ordering, something like a float, where most of the values are good, but if I've got a nan does not behave sensibly according to these because a nan is neither equal nor not equal to itself. So we can use a different category to indicate I don't have the full strong ordering relationship that you might want to depend on. And all of these turn into types that can be cast to bool appropriately. But because they're distinct types, we can take advantage of that in our overload resolution for our algorithms that care more about having certain properties. So to an extent, Spaceship is over-engineered to support all this, but in practice, C++ is a language where this level of detail turns out to really matter. It's about as far as I'm going into Spaceship on this. Again, hopefully there'll be other talks around elsewhere that will delve in a bit more detail. So that brings me around to the actual implementation of the data structure itself. Strategy 1, this is my traditional strategy I've been using since C++11, where we inherit from a pack expansion of wrapper classes and end up needing 1 extra layer for indirection to get the indexing. The idea is something like this. I have class tuple, derives from tuple data, derives from a pack expansion of tuple members. How do we end up at this structure? The basic idea is I want to write something like this. Tuple just derives from types ... That has a problem as soon as someone gives me an int, because I can't derive from a fundamental type. So we solve that problem. We wrap the int. Yay, this works. And then my slide dies. This doesn't, because I now have wrap of int and wrap of int as ambiguous base classes. I can't repeatedly inherit from the same class. So, I want to wrap an index in type. And the index is going to number from 0 to n, and that guarantees each base class has a unique type, and now tuple int works. The problem is, where am I going to get index from? Because I just have a list of types. I need to construct a list of indices of the same length. That's where index sequence comes in, and that's where this extra base class comes in, just so I can deduce an index sequence in order to match my index to my type to get the right packet expansion. And this is the basic design of implementing tuple, and has been for me since C++ 11. I keep trying to say 03, but we don't get packet expansions till 11. So, and then we inherit the constructors and a bunch of other implementation details. Because I don't want to be writing constructors here, forwarding to constructors here, forwarding down. I'm going to do all the hard work actually in base and inherit those constructors in the main tuple interface. Implementing get with this type is really quite simple. First, I'm going to have a requires clause so that even empty tuples, this just works. I don't need any special cases. I will SFINAE out if you pass me an index that's out of range. And all I'm going to do is static cast to the base, and then say retrieve the value from that with my fetch value function in this case. So it's fairly simple. Slash to the appropriate index base, retrieve the value. My ideal version of wrap would look something like this. It's a simple aggregate. It's got the data member. I know how to find that. We're done. What problems could there be? Well, when we get to quantitative implementation, we get things like, well, I don't want to pay for storage for empty members if I don't need to. And this is where lots of implementations will start using the empty base class optimization. But the empty base optimization has issues with unions and final classes, so you have to be using a bit of template chicanery just to make sure you switch from aggregation to inheritance at the appropriate time. Then, if the thing is implemented through inheritance, my fetch function, access function has to say, well, if it's an inherited type, I return you the base, otherwise I return you the data member. So I've now got to start branching and handling all these different cases of how to retrieve the actual value. We also have awkward corners with, because it's an aggregate, I can't initialize it using parentheses. I have to use curly braces unless I'm copy constructing or default constructing. So any of those constructors that want to say, initialize with this element value, nope, can't use this. I have to actually go off and write those constructors just because aggregates use a different syntax to initialize with. And finally, part of the tuple API, if I've got a tuple of int and just declare tuple int x, x.get of x0 will have the value 0. I do not have a default initialized int that is not initialized. It requires value initialization of every member, which again would require me writing constructors here, which gets away from I want a nice, really simple wrap. This is how it looks like in C++ 20. I'm not going into all the complexity of the C++ 17 version. That was 2 years ago's talk. Now we have this new attribute, no unique address. And that effectively will apply the empty base class optimization in place here. So if T is an empty type, this will be as if everything we're using the empty base optimization. Likewise, I could do this in C++ 17, but with all the other concerns, there was not much point. I'm going to, by default, value initialize the member. So if I don't give you any initializers, the whole thing is value initialized, so and it will be 0. If the type has a default constructor, it will call it. One of the other big changes coming for 20 is that aggregates will now support initialization with parentheses, just like they support with the curly braces. And this was actually motivated by trying to support things like a vector of standard array. Because when we go through to construct the array, we go through allocated traits we call the construct function. The construct function is effectively going to be calling new, which passes these things with a parenthesized list, so aggregates like standard array cannot be emplaced in a standard container. You can have a vector of arrays, but all you can do is copy whole values in and out. You can't do things like emplace to deal with members and so forth. So that was the motivation for putting the parenthetical initialization for aggregates there. Turns out to be exactly what we need to make this work for tuple as well, though. So that's quite neat. And again, now it allows all my derived classes to just default all the operations. Rule of 0. I've got nothing to write. So that's kind of cool. The one thing I didn't see on my slides, I've possibly got coming, is the other problem we had here in C++ 17 is because aggregates had to use the curly brace initialization, when I passed a narrowing conversion through my constructors, that would suddenly become a hard error, whereas the tuple API is supposed to accept it. Because when we defined the rules for brace initialization, we said that's going to outlaw narrowing conversion. So that's just another corner case that now I can go here with regular parenthetical initialization, those problems all just go away. So big simplification for tuple in C++ 20 here. And again, my access function is now as simple as can be. I just return .data because I have only one access pattern I have to worry about now. So I don't have to go off and write that other function and put it somewhere funky. So that's kind of nice. So falling over here. And again, we probably want to do something like adding support for comparisons. We can default these and allow everything to default further up. So just as it got simpler, different language feature means we bring back some of the complexity. But that's life with C++. So we're making progress now. We can default our copy constructor, default constructor, and our copy default move constructor. We've got this funky explicit thing that I was speaking about before that says this constructor is going to be explicit if any of my bases or members constructors invoked through this would also be explicit. Now, does everyone understand why explicit matters for constructors with other than one argument? Because explicit was clearly added to avoid accidental implicit conversions when passing arguments in C++ 98. C++ 11 actually gave explicit a meaning when you have multiple or 0 arguments in your constructor. And it occurs only when you start using the new brace initialization and say, I don't need to tell you what type I'm brace initializing because I'm calling a function, and the function knows its argument type. So I'll just give you a brace initialization list, and it says I construct the appropriate thing from that set of parameters you gave me. Or I return a brace initialization list because it knows the result type that it's about to try to construct. In those cases, if your constructor is explicit, it will reject that. Whereas if you don't have explicit there, that C++ 11 syntax will just work as is. So it's an awkward corner case, but because tuple is supposed to be a very generic wrapper, we want to replicate the behavior of the thing we are wrapping. We want to propagate the nature of the explicitness. And this is how we write it in the C++ 17 standard. Explicit is a funky macro in the standard that says, create enough extra constructors so that one will be explicit, one will not be explicit, and the right one will be found, and the other one will fall out through your various template chicanery tricks. Which gets harder and harder as you start dealing with things like the default constructor, and there's no obvious template parameters to hang off. So that's a fun problem to solve. Okay, this possibly could have done with being a slide earlier than the one talking about explicit, but explicit specialization for empty tuple, just as an aside for things I'm not showing, simplifies trying to deal with requirements that I've got all these constructors, and I've now got multiple ways to spell the default constructor if I've got an empty tuple. And rather than trying to put extra disambiguation rules in all the requirements and so forth, an empty tuple is really simple to implement. It's an empty type with no members. So I just declare the empty tuple and the constructors, and we're done. Even get doesn't do anything because the index is never the right size. Defaulted copy constructor has been cleaned up in C++ 20, and it affects tuple, it affects parent, and a few other things. If I have something like the old auto pointer that we removed in C++ 17, but you are still allowed to ship if you want, the defaulted copy constructor, because it was declared const tuple ref, wouldn't be copy constructible with an auto pointer. C++ 20, we finally fixed that in the compiler rather than the library to say, if I default the copy constructor, and I can see one of my bases or members has this funny other signature, I will change the signature you gave me to be that one. So it just propagates the right behavior through. So yes, tuple of auto pointer will again work in C++ 20, thanks to compiler fixes, as long as your library hasn't removed it. This turned out to be really important for us at Bloomberg because we do have some types that use this semantic because we still have some C++ 03 compilers and have to bridge the gaps. The other neat thing, default constructors now get the correct exception specification and so forth because why wouldn't they? And again, you just look at these exception specifications of all the bases and members. You don't need to see the definition if you're just going to default all these things through. And const expr and so forth. But what about the explicit markup? This is what I already just mentioned, sorry. So, in C++ 20, we can actually embed this directly in code. We now have the ability to say explicit can have a conditional expression, and that tells you whether or not that constructor is explicit. And we also remember in 17, we tightened up all the SFINAE constraints to say this thing is copy constructible only if all of its bases and members are copy constructible. We expressed that with the requires clause. So the requires clause says I'm available only if all of my bases and members are copy constructible, with my parentheses for my redundant fold expression. And my explicit says if I'm not convertible, but I am copy constructible, that's the case where I want to be explicit. So if that's true for any of those things, I'll do the pack expansion for is convertible, and then negate it and say, okay, same deal. And now I don't need to play around with clever template tricks and write multiple overloads. So as an implementer of these things, this is really nice. As someone reading the library API, you're actually looking at code that expresses what you want rather than trying to decode lots of crazy template signatures. So that's kind of helpful. A similar idea for the heterogeneous perfectly forwarding constructor. Similar constraints is constructible for these types and is convertible. Same idea for pretty much all 9 of those constructors that were then going to be multiple duplicated. Assignment. We can kind of get away with defaulting it, mostly. We have a problem with references, though, because if I've got a reference member element in my tuple, the defaulted assignment operator is going to be deleted, which is not good. We want assignment to, in this case, actually assign from one reference into the reference at the other end, not rebind it. Simply say, well, I've got two values. This one can be assigned to, so just read that value and assign it through that reference. And that's important when we start using features like tie. It's a very specific design feature of tuples that we want to be able to have references have that behavior. So that means that we end up having to implement an assignment operator And because we're implementing an assignment operator, and specifically a move assignment operator, that deletes the copy constructors and move constructor unless we explicitly default them. So we end up losing rule of 0 and have to have rule of 5. So that comes back to, well, I want to try to get back to rule of 0. Here's how I would implement wrap now, so that wrap is going to do the right thing, and therefore tuple data that's just assembled out of wrap can now just default and get all these things for free correctly. So we provide this partial specialization for wrap of references, and another one for R-value references, and then everything, again, should just work. So general notion of the simplifications I've got going here. The requires clauses be enabled if and other SFINAE tricks. They should be much easier for the compiler to parse. Hopefully they're a lot easier for us to read, and they give us proper vocabulary to describe what we're doing. No unique address gives us the empty base optimization in a much more useful, manageable manner. And the wrapper simplifying to an aggregate just simplifies an awful lot of machinery we used to have to do at that level. So we get a much simpler implementation of tuple out of this. Surprising corners I found doing this. And so the explicit specialization for the empty tuple we discussed. Inheriting the default constructor helps me correctly deduce explicit. Whereas if I were to try to define equals default this in the most derived class, if it was to equal default it in tuple rather than inherit it from tuple data, it doesn't get the correct explicit. So we actually want to inherit the default constructor, which is a really surprising little corner. Has everyone followed what I'm saying here? Because this is a bit subtle. Especially now I'm tripping over my teeth again. So the explicit bool rendering also applies to the default constructor. When we equals default a constructor, we do not pick up the defaulted of the explicit. That still has to be explicitly declared each time. And because I went through all the work to get that right once in the base class, I want to inherit that. And it turns out that with the new rules for rewriting inherited constructors, we do not get the rule of 0 default constructor that way. Instead, we get the inherited default constructor from the base. And that does the right thing we want here now that explicit bool has been added to the language. So it was an interesting corner I stumbled over when I was playing around with this. And that, again, is a big reason why we could get away with an awful lot of delegation now, where we had base as a member, rather than inheriting from it and then just pull everything appropriately. It changes how you implement some of the forwarding functions, but it gets away from this strong coupling of inheritance is the strongest coupling you can have in the language. And it's nice if you can take a step back from that. And another trick I was doing was I was trying to treat pair as a variadic type with the requires constraint that the size of the parameter pack is 2. And that then let me use a lot more of these generic idioms because I then have a parameter pack I can be passing to my shared code between tuple and pair and array. So that, again, that was just a neat implementation trick. We didn't see any slides on that. That was just something I'm mentioning in passing. But we also have the idea of if I want to move away from inheritance as being a too strong a coupling between my class and its implementation details, I could try implementation strategy 2, where I have a front and a tail. Front is the first type in the parameter pack, and tail is just another tuple. So this is the classic recursive tuple definition, now done as members, because now I have no unique address. I don't need to rely on inheritance to do all that squashing out of the stuff. This actually becomes viable to really eliminate that whole inheritance tree. It means I now do need to implement my default constructor, with horrible explicit and the requires on and default constructible, only for my members and bases are default constructible. But I can default the copy and so forth. The problem here is it's not that it doesn't work, it's swings and roundabouts, which implementation do you prefer? I no longer have a single clean parameter pack because I need to pull out first type in addition to the tail. So, some of my code now looks a little bit more complicated. Does everyone see what this is? Hands up when you've figured out what this is. I'll give you about 30 seconds, and then I'll try and make it a bit clearer. I'm seeing a couple of hands going up. Okay. That is what we're actually trying to declare. It's a declaration of that constructor, and everything else is padding describing constraints on that constructor. So concepts are great, SFINAE is great, but sometimes it comes at the cost of readability. It can be really hard to drill into where some of this code actually is lurking. But we can see we've got the requires is constructible first, type, and tail. We're basically duplicating each of these constraints that we had that were simple when we had just one parameter pack to worry about. On the other hand, implementing this is really simple. Construct from front and other from tail. If we've got the heterogeneous version, it's just perfect forwarding. The implementation side is really simple and significantly smaller than the declaration. So this is still an interesting avenue to look at. How easy is it to implement get on this form? Any ideas? Because now I need to do this whole recursive, I've only got one and I have to walk through the tail. Well, turns out get is really simple. If my index is 0, return front. Otherwise, get on my tail. And if const expr means this just does the right thing, my result is decal type auto, because it's whatever is found by that appropriate walking through the branches. And just to compare, this version does a nice slicing down to the base from the original parameter pack version, but I had to pull out my result type in order to know the right type I'm returning and have it in the declaration. So, which one's simpler? Well, this one's going to optimize more easily because the slice to base works quite well. Most compilers are going to still do a good optimization on this for suitably small tuples, because this whole recursive thing is a compile time recursion. I don't need to keep, storing all those, in directions. I can just, return you the straight answer. So tuples of size 8, 16 is probably going to be as efficient. Tuples of size 1023, probably not so much. I doubt very much that will be inlined all the way down. But compilers get better at these things all the time. And if it turns out that this kind of lookup is important to inline, compilers are going to get there. Special cases when they see this pattern to allow a much deeper recursion on their const expr inlining. And as we get back to the end, here are some of the things that I didn't cover. Allocator-aware constructors have terrible SFINAE constraints in the standard, as in they don't have any. So all those nice things about concepts and everything else that helped us narrow our conversions and make sure that is constructible as a trait gets the right answer do not apply to the allocator-aware constructors. Whether we can fix that up, I don't know. Basically, it means that your empty tuple, if I ask you, are you constructible from allocator argt, allocator, and as many arguments as I like, the trait will say yes. Then I will instantiate it and I'll get a hard error. So that's unfortunate still. On the other hand, trying to implement these things will get a whole lot easier using makeobs using allocator, which basically encompasses all the funky rules we have with allocator traits to say, if this type can use an allocator, pass it in the appropriate way and construct it in the appropriate way. Otherwise, just do an in-place new. So that's kind of handy. That will make us an object. In order for everything I've shown you about using aggregate for the wrapper type, though, I'm relying on aggregate initializing base classes using the syntax and guaranteed copyalism, saying that allows me to do that initialization in place. Otherwise, I'm paying an efficiency gain. And I do not know whether I have the guaranteed copyalism I need to make the allocator aware parts work. So it might be that we have to take a step back to get the allocator aware behavior into tuple, which would be a shame, but I've not got my hands on a fully working C++20 compiler yet, and I don't grok the standard at that level to be 100% sure either way. So that one, I'm afraid, is left as an exercise for another day. I'm just coming to the end here, so I'm about 10 minutes early. Some closing observations. Interface implementation of tuple now contain an awful lot of verbiage for the compiler and other tools rather than necessarily the human reader. Generally, I'm using a cheat sheet, which looks more like the standard than the actual code when I'm trying to figure out what these things do. Whereas in the past, my primary documentation of reference would be the header file with the actual declarations. So this is leading me in the direction of something John Lakos is very fond of promoting, that your contract is written in plain English, and whatever you write in the header file with it is extra communication for the compiler, but to understand that contract properly, you have to go away and read the actual documented specification in English. And that's often where you'll see a simplified form of these now that you can actually understand to say, those are the constraints that are coming in, those are the requirements, as opposed to finding that 3 or 4 tokens in the big 17-page token soup. And again, remember, everything I was showing you just used concepts today. We didn't have runtime contracts on top of that, potentially growing those declarations even further. So it's less clear to me that today, source code is my documentation of choice. It's the master, it can't be wrong. It's less clear to me that that will be the direction that's good for me in the future. And modules are all potentially moving away from that notion anyway, as modules, as I say, they're not header files. So how do we distribute documentation through module systems? Maybe we're going to rely a lot more on documentation generation systems, as I'm sure a lot of you already rely on today. And that is as far as I go. Any questions?